I'm going to talk about something. This is well, so what I've shown so far has been fundamental load pull. It's load pull at the fundamental frequency. For GaN, for any high power transistor, the behavior of the for any high power transistor, if you're operating in compression or near compression, the performance you get depends on the harmonic reflections as well. So you need to investigate the harmonic reflection coefficients, and that's what this setup does. This is actually, you can do this sort of thing from the standard built-in ADS design guide. So if you go design guide, load pull, and then under one-tone load pull simulations or one-tone load pull simulations, Z-sweep, load harmonic phase sweep has setups where you can sweep the harmonic phase and look at performance versus the load phase at the second or third harmonic. But this one is a little different. It has a multidimensional sweep of the second harmonic reflection coefficient at the source, second and third at the source, and second and third harmonics at the load as well. And I'm sweeping around a high reflection coefficient value set by S load mag and S source mag, and I'm fixing the load fundamental impedance. So before I do this, I want to show one other thing that I think is important to think about, and that's that in this setup for the XDV simulation load pull, this optimization actually does at the start of the load pull, it optimizes the source impedance at the fundamental to try to get a good power transfer, a good impedance match at the input. So it steps the load, and then at the lowest, or at a relatively low input power, it attempts to optimize the source impedance at the fundamental to get a good impedance match at the input. So there is a little bit of adjustment of an automated adjustment of the impedance at the fundamental, the real and imaginary parts. So that's different from the other setups that I showed earlier that are part of the original load pull design guide. They have a constant source impedance, whereas this has an optimization of the source impedance. So this, and I was just going to mention, this setup has the harmonic phase and amplitude sweeps. And then you can do two setups here. One version is you can tell it to optimize up to or sweep the source power up to a specified power delivered, or you can tell it to sweep the source power until you reach a specified gain compression amount. So if it says P del, then it's going to try to hit this target impedance that you specify. It's going to sweep the source power to the target impedance. Otherwise, it'll sweep to the XDV gain compression point. So this one is, say, for XDV gain compression. Okay, so it's a lot of data. It can generate a lot of data. I've removed the data. So let me see if it's in this one. It may not be in here. Okay, so this one does have it. Okay, so this shows that there is some variation in gain. This is all all this variation is in the gain and the phase response. All of this variation is due to the particular combination of harmonic source and load reflections. So this allows you to investigate how the performance varies as a function of the harmonic reflections. Okay, and usually it's the load second harmonic that has the biggest effect, and that's so I'm moving the second harmonic load around the Smith chart with my marker, and then this black line corresponds to the combination of source and load impedances that I've selected with these markers. So this is one way to do it. There are other examples that I have that include this sort of analysis. Okay, I have a two-stage load pool example, which I'd like to show briefly. Let's see. This was an example that I worked on at the request of a customer who's actually in the audience today. So it's, I think it's a useful example, and but what it does is I've made it a generic example with an LDMOS device in it. This is the same LDMOS device, but you can set this up. It's a two-stage design. You could add additional stages, but this allows you to run a load pool simulation using a two-port tuner, and you can run a load pool, say for stage one. In this case, we can we're able to select the loads as before using the graphical load pool data display. And you can actually do similarly, you can do a source pull the same sort of way. But the results are similar to what I showed earlier, at least for the load pull. And this allows you to, say, experiment with say interstage matching networks. You can have an ideal load presented to the first stage and an ideal load or source impedance presented to the second stage, and you can insert some insertion loss and experiment with how a multi-stage design would work, and look at which stage compresses first and how much and things like that. So the results look like of a two-stage simulation look like this. Let's see. So in this case, I'm running a power sweep. I'm taking the two-stage design where I've specified, say, an optimal load for each stage and an optimal source impedance for each stage, and then I can run a simulation in which I sweep up to the XDB gain compression point, and you can look at data like the overall power output efficiency, phase versus output power, bias current of each stage. You can look at the thermal dissipation of each stage, the AM to PM distortion versus output power, as well as of each stage. So the red traces are the AM to PM from the first stage, or the data from the first stage. The blue is the data for the second stage, and then the black is the overall. So you can see where the gain is, whether the compression is occurring in the first stage or in the second stage. For example, this is AM to PM distortion versus output power, thermal dissipation versus output power in each stage. But I think this is a very practical design example, which would be useful for multi-stage design. It's also possible to, like, if you have a design where you have, say, several FETs in parallel, and you have the outputs, you have some sort of a combining network. So this would go to here. Let's say this is the output stage, and you have a combining network, and maybe you have more than two, maybe you have 4 or 8. You can see, using the Winslow stability probe, you can see what the load is seen by each different transistor in parallel. It's possible to do that. So you could run a load pull on each transistor, see what the optimal load is that it wants to see, and then when you combine them together, you can still see, is it really getting the desired impedance that you want? And I'm working on an example that shows how to do this, but I'll publish something probably within a few weeks. But that's possible to do using the WS probes, which are the stability probes. Okay.
Andy?
Yes. Yes.
So can you show the four block schematic?
The two. Yes.
Yeah, two-stage amplifier.
Yes. This one.
So will you simulate the whole block simultaneously, or just to divide each stage load pool and then plug in that load pool data into this schedule?
Okay,
just to show us your procedure of the design.
Okay, what I did was I ran a load pull simulation on the first stage. This is load pull on the first stage, and then I did a load pull on the second stage. So these were done separately. And in this case, the second stage, I have the scale factor. So this is a much larger device, because I have scale factor set to 12, whereas for the first stage, it's set to 2. So I have a much larger device for the output. You can set that to whatever you want, and I just have that. That's passed into N, which is the number of what is N? I think N is the number of fingers. So the stage 2 is much larger. So I ran a separate load pull of each stage separately, And then I did, in this one, I can set the load here to be the optimal for the first stage, and I can set the load here for the second stage to be optimal for the second stage.
So the number you get from the previous stage, the result or
The result.
automatically or the manual?
It's just the result. I looked at the data display and said, okay, this is the best value, and I'm putting that in, and undo that. That's here. So I have. I got this value from the first stage load pull, and I got this value from the second stage load pull. I just entered it. So it's not doing another load pull here. It's just holding it constant. And then we did a power sweep, and you can see the gain compression and the thermal dissipation, things like that.
But indeed, this schematic, can you re-optimize?
It could be, yes, you could re-optimize, yes, certainly. Yeah, it would be more complicated setup, but yeah, you could do a re-optimization of the load impedance here. You could make that an optimizable variable, yes. Yeah, you could certainly do that.
I don't know if it is possible, but in some setup, once we get on each stage load pull, and then automatically the result is plugged into this two-stage amplifier, then it will be very simple to accomplish the goal.
Yeah, you could run a load pull, look at the load pull data, and then write it into a file, and then this could be read in from a file. I could have a data access component on the schematic and just read data from that file directly. Then you wouldn't have to by hand type it in. Yeah, that's possible to do.
And also, as you mentioned, this is a very critical and useful for us. So will you share this workspace with audience?
Yes. Yeah, I will. Yes, this one. Yes, it's already on the Knowledge Center, but yes, I will share it. Yes. Yes. Yes.
How can you set up the source sequence of the second stage of source sequence because of you already simulate the first stage of load pull. You got the load impedance of there, and how can you set up the source sequence in second stage?
These are independent. These are ideal components. They're equation-based components. So I can set S22. I can set the reflection coefficient looking this way, independently of what's connected to it on the input. It's an ideal component. So it's kind of like the way I think about this is if you had a two-stage design, and so let's say we've run load pull on this output stage, we've run load pull on the input stage, and we know the optimal load, and we know the load impedance, and we know the optimal source impedance. We looked at the data display, and we figured out what values we want for the optimum, which values we want to use. And we did the same thing for the first stage. And what this is doing, obviously, this is not a real amplifier. It's not real. It's a model. So what this simulation does is, if you could come up with a network, say an interstage network that presents the ideal load that this stage wants to see and simultaneously presents the ideal source impedance that this stage wants to see, and you also have another network that presents the optimal load and similarly the optimal source for the input, what's the performance you would get from it? So this is kind of like a maximum, like best case performance. You can't get this in reality because you probably cannot create a network, a real interstage matching network that gives you the ideal conditions. But maybe this is kind of like, okay, this is the best that we're going to get. So maybe this is useful as a tool to see what's the best case that you could get from these transistors and from these from the load pull that you ran. And then, okay, that's the best case, but now we have to replace this with a real, like a more physical matching network. So the performance is going to drop. It's not going to be as good because we're not going to get the ideal impedances anymore. But at least this tells you, you could use this to see what the upper bound is. Okay, this is the best we're going to get. If that's not good enough, then you need to come up with a different design or change the sizes of the transistors or use different devices or do something else. So that's the way I think of it.
Another question. You mentioned about the Winslow probe for
Yes.
checking the impedance of each stage.
Yes.
I just use the Winslow probe for just Nyquist analysis, but can you use you got some more better impedance with that probe?
Yes.
Just briefly mention about that.
Well, yeah,
Compared to other probes, ABS library.
yeah, I think that the Winslow stability probe is useful not only for stability but also for checking the impedance here. So you could use the Winslow stability probe for optimization as well. If there's some optimal impedance you want to present here, the Winslow stability probes could be used in an optimization to try to get to that impedance.
Later, I want to learn about this.
Okay.